Okay. So, oh yeah, well, some of you asking me offline and asking the TH, what about that, right? So simply, you'll find that in most of the slides, I have this slide at the beginning. Like if someone was to do a further reading, HB is Hennessy and battery symbol, right? And this is chapter 5, and then you can say or I guess this is the fifth edition, this is the appendix B1, B3, and then chapter 2, 1, 2, 3, right? If you want to do further readings, right? Okay. So the topic we're discussing today is very, very important for computer architects, especially nowadays, because most of the innovation that is happening in the computer architecture and most of what industry cares about, as well as academic researchers, is in the memory hierarchy, not in the processor pipeline itself. The processor pipeline is almost a mature design right now. There is a very little innovation into it. And this is why, and also most of the bottleneck is coming from the memories because of the massive data you need to deal with. Think about machine learning, graph processing, all of these things deal with massive data amounts, which means you need to handle them very carefully in your memory hierarchy, including caches and main memories, the lecture we're going to cover afterwards. Good. What we're going to cover is, well, some of the fundamental concepts that apply both for caches, main memories, or even any type of memory. For example, the discussion of speed versus capacity. And then we will delve into the cache organization architecture and how does this fit within the whole memory hierarchy. And then later on, we'll talk about main memory, but this will be after we finish the cache topic. And this is the topic for Lab 4 as well. And then virtual memory afterwards. So why are we discussing memories? Why memories are important? Because you can make your CPU, your pipeline, run as fast as you can. So we have taken pipelining concept, and then we have also covered in the high level some of the more advanced concepts like superscalar, out of order, and those we're going to revisit later on in more detail. But the main idea is that we're trying to improve our performance, and we're focusing mainly within the CPU, right? How can I really make the pipeline better? How can I replicate the pipeline? But the problem is, one step back. And then we have also seen the reflection of this in performance. Like, for example, how can I improve the running speed by reducing the clock build, having multi-cycles and pipelining, right? And then also, how can you improve the effective CPI, cycles per instruction, again, adding pipelining, and then superscalar, out of order, VLIW, and then multi-core, multi-threading. But then, do all these improvements. At the end of the day, according to Amdahl's law, going back to the performance lecture, if you make the common case very fast, so if you accelerate or you make part of your program very fast, while the other part is slow, you will eventually be bottlenecked by the slow part, correct? So at the end of the day, the CPU can run, which is written here, you can compute only as fast as memory. Because real applications, you need to bring in data from the memory, process them, do some computation on them, and then write them back, right? And then you bring another data of memory, compute on them, and then write them back. So if I'm not able to fetch data from the memory as quick as I need, as quick as the compute engine, which is the processor, then eventually I'll be waiting for the data to come from the memory, right? Multi-core, as we have seen also in the multi-threading part when we were filling those parts of cache misses, helps a little bit with mitigating this by saying, okay, if the application right now is stalling because I'm bringing something from the memory, maybe another core or another application can do the computation right now, right? But there is also a limit for this because all those cores and all those applications eventually will need the memory. So if the memory is very, very slow, then in reality, you'll also be bottlenecked. Good. Today's main memory latency is more than 33 nanoseconds. We will see later on the some slides that in fact the access latency of the memory is 100x, and this is in your laptop right now. If you go to the main memory, you might suffer 100x latency, 2 orders of magnitude latency compared to an add instruction, for example, right? So if you write a very simple, one of the benchmarks we have in the labs, the vector addition, right? If you bring in 2 vectors, 2 arrays from the memory, and then you add them, the add operation is very simple. If it takes, let's say, 1 cycle, effectively, and your main memory is taking 100 cycles, this is a memory-bound application, right? So you are bottlenecked by the memory. Make your add as fast as you can. Well, doesn't really matter, right? And we have seen this from the performance lecture again. If we take all the instruction types and then multiply with their effective cycle latency, we obtain the average CPI. So if one of them has a very huge latency, you can do that math. Assume the memory is taking 100 cycles, the arithmetic is taking 1. Eventually, your actual performance is limited by this memory access time. Good. What are we looking for? So simply, I want a memory that is, well, ideally takes 0 time. Go bring the data, takes just 0 time, and also it has infinite capacity, right? I want to store as much memory as I can, right? But those two goals are just theory, right? They are almost impossible. Let's say I even want my memory to operate at the same processor speed, which is also not attainable right now. Most of the memories are in fact running at lower speed because they use a different technology. We'll see later on that main memories, for example, use capacitors, and like the cell itself is a bit different because of the cost. And then the memory cannot be as large, right? Like how many total memory you have right now in your laptop? 32 gigs, 16 gigs, 128 gigs. And I'm talking about main memory, right? Not even the cache hierarchy. If you look into your cache specs, you will find that your L1 cache, the level 1 cache might be 16 kilobytes, 32, 128 maximum might be. Level 2, well, kilobytes as well. If you have a level 3, if you have a very advanced laptop or a desktop, and you have a level 3, it might be megabytes, right? But if you open any practical application, gaming, for example, if you are into gaming, you need gigabytes of data, which means you will not be able really to put that application data into the cache, right? So you have to go to the main memory, which is way slower, right? So this is more like a slide from electronics, because sometimes this topic, I would assume it's covered in electronics courses. There is a big difference between SRAM and DRAM. Did you see that before? Do you know what is an SRAM? How do we put together a memory cell to store 1 bit? Right? It's like 6 transistors, you put them in a certain format, right? It's called an SRAM cell, right? And static RAMs, like composed of 6 transistors, because these are 6 transistors, well, they consume area and they are costly, right? So you cannot really have gigabytes of them. This is why caches, the ones that you have closer to the CPU, are in megabytes, as we were saying, kilobytes. Why? Because every single bit is composed of 6 transistors. So they are very costly in terms of area, right? If I store 1 bit in 6 transistors, think about 4 megabytes will consume a huge area, right? And we have some pictures later on to show that. And then caches, well, they trade off area, so they don't care too much about area and cost, but they give you a very high speed access time. So SRAMs, you go there, you get your data in few cycles, right? It varies in real machines, like for example, an L2 in an Intel laptop might take 4 cycles, an L3 might take 10 cycles. An L1, usually everyone is trying to aim to be between 1 and 2 cycles, right? To make it very, very fast. I go to the level 1 cache, bring the data as if it was in the register. And it's volatile. Volatile means, when I say volatile memory, what does it mean? You know? Yeah, it's lost when what happened? There is no power. Yeah, if you shut down your laptop, your DRAM is volatile, your cache is volatile, your only data will be on the disk, right? This is why when you boot up your machine, in fact, it loads the image from the disk into the DRAM, right? It takes some time to boot up. Good. So the summary is SRAM is very fast, but we can only have very few out of it because of the cost. 6 transistors to 1 bit. On the other hand, the technology that is used for the main memory, the over-chip memory, the DRAM, it's called dynamic RAM. It's consisting of 1 transistor and 1 capacitor. And it's optimized for density. This is why we can have and the cost per bit, which means we have gigabytes of that. Right? This is the reason why, if you ever wondered why you can have gigabytes of DRAM, but your caches are only very small or tiny, that's because, well, this is very costly. It's optimized for speed, but this one is optimized for cost. So you can have many gigabytes of that. Right? Some server machines, you have terabytes of DRAMs. So it's optimized for density and capacity, but it's very slow in access time. Right now, it's like 33 nanoseconds. Here it's written like 40 nanoseconds in internal access. It's a bit. This applies for DDR3. Right now, we have in the market DDR4 and DDR5 soon, right? So those ones are in the range of 30 nanoseconds. well, DRAM also requires refreshing, as we will see in the DRAM lecture, but forget about this for now. But both are volatile memories, which means when you lose power, you simply lose your data. The non-volatile storage we have in our machines are usually the magnetic disks, the SSDs, the flash RAMs, etc. Right? So it's completely different technology, and we'll see later on how we give the illusion to the application that we have infinite memory by using the virtual memory concept on the disk. Right? This is a lecture on its own. So this is a figure that's showing you why we have a real memory problem in our current machine. So it's a retrospective study from 80s up to 2005, showing simply the performance scale over time, right? How the performance improved between CPUs, which is basically the processor pipeline, and the memory. Good. We will see that the more you move forward, in fact, the gap is increasing, right? Why? Because the CPUs are leveraging that Moore's law way faster. The performance is almost doubling every 2 years. And you will see that, well, initially in the 80s, they were running almost in the same speed, giving the same performance, which means memory was never a problem. But then later on, the gaps keep increasing and increasing and increasing, right? Right now, in fact, the gap is way larger than this, right? What is this gap? It's the performance. What does it mean by performance? Well, the execution time, for example, on an application, or well, in memory, we measure it by bandwidth or throughput, how many bytes you get per cycle. In the CPU, how much compute you can finish in a cycle. Okay. Yeah, this is a very famous quote from von Neumann. Von Neumann is the one that, in fact, invented the machinery logic as we understand it right now, right? The data flow model of the CPUs. And simply, as I was saying earlier, ideally, we want to design an infinite large memory capacity, so that basically all the time my data is there, and I want it to be zero access time. Go ahead, bring the data, right? But those ideal things don't exist in real life, right? You need really to have a trade-off. To address that trade-off, people came up with the idea of a memory hierarchy. If SRAMs are very fast, but we can only have a few capacity out of them, and DRAMs are cheap, and we can have large capacity, but they are very slow, what can we do is we have a hierarchy of memories, such that the CPU, closer to the CPU, you use the SRAM technology to have a cache hierarchy that you can access very fast. But because it's very small, you will not all the time have your data there. So you need to go to the main memory to bring it. But by having a hierarchy like this, you are giving the illusion that your data is almost, or your hope is that you always hit, you always find your data in the closer level to you, right? So in our current machines, we have a hierarchy, multiple levels of memories, right? The closest to them is what we discussed earlier, which is the register file, right? Register file is in fact the very first level of memory that you have closer to the pipeline. It's in fact tightly coupled to the pipeline. All the instructions go to the register file to bring in the operands, right? Register file is a form of a memory, right? Correct, but it's close to the CPU. And then, well, if you remember the data and control path figure we had, in addition to this, we also had the iFetch, like the instruction memory, the iMemory, and the data memory. Those are usually the L1 memories, the ones that are close to the CPU, is the second level. Good. So we are building this hierarchy with the idea that if you are closer to the CPU, what we call the upper components, you want to be fast, you want to be small because you are very expensive, and you are using SRAM technology. The lower components, the ones that are further from the CPU, main memory, for example, or the disk, they are very slow, but they can have big capacity because they're cheap. Good. And by having this hierarchy, this created another important topic in computer architecture that is interconnected, right? You have buses, you have network on a chip, all of this to be able to connect those hierarchies and connect multiple CPUs to the hierarchy. Good. Okay. Yeah, so the idea here is you want to access your closer level to the CPU most of the time. Why? Because those are the fast ones, right? For example, if my data is always in the register file, that's great, right? Because we assume that you can access the register file during the decode stage, bring in your data. You don't need to access something off the pipeline, right? So it's very, very fast. But again, this doesn't happen all the time. Yeah, if you look into a real hierarchy here, so in that bus figure, we just had it as an abstract memory level 1, memory level 2, etc., etc. But here, we started really putting things in their own names. The level 1 that is in fact with the CPU is the register itself, right? This is the register file. And then part of the control and data path, we have the instruction cache and the data cache. And then afterwards, we might have another level of memory called L2. We might even have L3. Some servers even have a fourth level of cache. But then you have the main DRAM, the main memory. This is off a chip, right? You see that all of this, in fact, we call it on a chip. What does it mean by on a chip? I don't know if any of you had the experience to assemble their own desktop, for example, but a while ago this was a hobby that they would like to do, right? So if that's the case, then you go and in fact purchase the, I don't know, like Intel i7 chip on their own. So you go and purchase it separately, and then you purchase like an MSI motherboard, something of that sort, and then you put the CPU in the motherboard. The chip you buy, like the Intel chip you buy, this is what we call the chip. This has the processor and has that cache levels, right? This is the green part here. Right? But then the main memory, well, to be able to put memories in your desktop, you go to Amazon or any other electronic store, and then you purchase the DIMMs on their own, right? The DRAM DIMMs, right? Those ones you plug into the sockets in the motherboard of a chip. So they are connected to the CPU through simply tracks, buses on the motherboard, right? These are those. That's why we call the main memory off-chip memory, because it's not with the CPU on the same chip. Why it matters if you are on the chip with the CPU? Because if you are closer to the CPU, you are way faster. You are manufacturing the same technology. It's an extra memory, it's very fast, right? And then after the main memory, you have the disk, which is a completely I/O device, right? It's something that 1000x more latency than access the register file, for example, right? This is very, very slow. Good. Questions so far? Yeah, so if we look into our legacy figure that we had earlier, so we said we had the instruction cache and the data cache. Those are the first level of caches. If I'm adding another, this is the register file, which is simplified to cover to the CPU. But then if I want to add another level of cache, I would connect the L2 to the instruction cache and the data cache. As you will see later on, if I go to the data cache, for example, I have a loaded instruction. I go to access the data memory. My data might not be there. Why? Because this data memory, assume it's 128 kilobytes, for example. And in the lab, you will sweep the sizes and see really how does this impact performance. Assume you're accessing a very large data structure, something that fits into 512 megabytes, while your cache is only in kilobytes. That means not all the time you go to the memory and you'll find your data. If my data is not in the data cache, from where can I obtain it? Well, from the lower level. In that case, it's from the L2. L2 is a larger capacity memory, right? So if this is in kilobytes, well, this is also in the upper level of kilobytes, sometimes 1 megabyte. Fine. It's a larger capacity memory, which can mean it can hold more data. But its access time is slower. Good? Because for SRAMs, for caches, the larger the memory, the slower the access time. So there is a trade-off. Good? Questions? Everything so far makes sense? Yeah. Okay, so if we look into, this is the i7 floor plan. If you look into it, you will find, in fact, can you highlight here some of the things related to the memory, caching in general, just to have a sense of how much area we are dedicating related to caches in modern chips? Can you identify any of the things that might be related to the memory on that chip? What is that? Yeah. Yeah, the L1 data cache, right? This is the D cache here. There is also the L1 instruction cache, right? Which is here. And then there is the L2, correct? Which is here. What else? In addition to the actual storage, there is also memory ordering scheduling logic, right? So there is something that tries to do scheduling to those memory levels, and it's also consuming considerable area, right? So you see many, well, I wouldn't say it's almost half, right? Or maybe 40%, 30 to 40% of that chip area is in fact dedicated to memory. Paging as well is dedicated to memory, as we'll see later on in the virtual page. in the virtual memory lecture. Good. So 30 to 40% of the chip is in fact dedicated to handling memories. Right. This tells you how important is cache and memory to the performance of a modern CPU. Then compare this to some of the old machines. So here I'm picking something that is very, very, very old, like 486. It only had a unified instruction data cache, so it's only 8 kilobytes. Here it's a PART1 machine from IBM that also had an L2 and some L3s. And these are old machines, right? If you look into some of the modern machines right now, something like the same Core i7, but in a more detailed way, that has the multi-core as well, not only the core. The part I showed you earlier, this one, this is the one core floor plan, right? This is one core, right? And the core has an L1 private cache and L2 private cache, right? But in an i7, we know it's a multi-core chip. If you look into it, we have 4 cores. Each one of them, in fact, has the L1 and L2 that we had earlier. But in addition to this, they're all sharing an L3, right? You see that the L3 is, in fact, consuming a very large area as well, right? And then there's also the memory controller I/O that we'll see later on in the DRAM lecture. Good. So in the Core i7, you have an 8 megabyte L3. In each core, you have an 246. This is combined L1 and L2. Good. Again, much of the chip area is in fact dedicated to handling memories. Now, one big question or observation, why in fact the memory hierarchy is the current adopted solution to handle the memory problem, right? This is known in computer architecture as the 1090 rule, right? And later on we'll see that this is known as locality as well. So the idea is that 90% of the static instructions account for the 90% of the executed instructions. What does it mean? It means that if you look into the instructions in your program, we find that 10% of the instructions only take 90% of the time. Why that's the case? It's an observation that we made earlier as well when we talked about branches and how we handle pipeline. Why, in fact, if I look into an application, this would be the scenario. Can you think of an example? Yeah. Many edge cases. Yeah, well, okay. So if you think about any of the applications that you also have in the lab or the ones we discussed earlier in the slides. So can you think of an example where the same instruction, the same exact instruction with the same program counter keep executing again and again and again? Under which scenario this happens? Yeah. Loops, right? In a loop, you go through, number of lines of code in the high-level C, for example, and you keep repeating it, right? And we said earlier, many real applications, loops and very large loops are very common there, right? Which means same instructions keep executing, which means if I try to quantify the execution time of this particular instruction, I have to add up those 2 iterations, right? So the observation is that in real applications, mostly 10% of the static instructions account for the 90% of the execution. Again, because there are so many loops are happening in real applications. Good? Oh, it's already written here. For data memory, so we're talking about instructions right now. Instructions were repeat. What about data? Also, the 1090 rule is that 90% of the variables account, in fact, for the 90% of the accesses. So some of the variables are very frequently accessed, right? Think about, for example, global variables or inner loop variables, where I keep repeating them again and again and again. So if I optimize for those, I optimize for a lot of the execution time, right? So there is a lot of repetition in our programs. This is using a key concept we have covered in the performance lecture at the very beginning of the course, that I'm trying to make the common case fast, right? So if the common case keeps repeating, if instructions keep repeating, and if certain data keeps accessed again and again, if I make the access time to this one fast, then the overall execution will improve a lot, right? So it's again, make the common case fast, right? Again, Amdahl's law. Good. And then this is basically the 1090 rule. And then locality is also very common in most applications. What do we mean by locality? If you think about an array, for example, right? If you look through an array, what do you really do? You simply go and bring in an index, like an entry, and then you process it, like add it or do something like, again, the vector addition example we have in the lab, or maybe matrix vector multiplication that we also have in the lab. You basically go through a loop, bring in certain data, operate on it. In the next iteration, what do? You bring in the second entry, the one afterwards in the array, right? And then in the third iteration, you do the same, which means you are moving in your array in a sequential fashion, right? This tells us that, in fact, if I was able, when I'm going to the memory, don't only bring element 1, but bring element 1 and 2, or 3 and 4 and 5. If I bring all those elements together, next time when I'm trying to access 2 or 3, I don't need to go to the memory, right? Or to the further memory. I only access the closer one, right? This is called locality. It's a concept, and later on we'll see, it's called spatial and temporal locality. If you access the data, most likely you're going to access it soon again. And if you access the data in the memory, most likely you're going to access the adjacent data to that data. Think of an array, for example, right? You access element 1, then most likely you're going to access element 2. If you access element 1 once and you do a lot of computation, most likely you're going to access element 1 again, right? Good. Questions so far? So these two concepts are very, very important into why the whole memory cache is working right now. And in fact, people are challenging also this concept right now because of some of the modern applications might not have a lot of locality. What do we do to optimize the memory? But still an open problem. But our current machines, all the machines you have, no matter whether they are embedded, tablets, laptops, they are leveraging this locality concept. Good? So again, what is temporal locality and what is spatial locality? Temporal locality, the easiest way to understand is, say, if I'm accessing an array element right now, most likely I'm going to need it later on. Think about it. For example, I need to bring something from the memory, loading this data, operate on it a little bit, and then, or maybe first, before I load it, I need to write it first, right? So you need to store to a certain memory location, then later on bring this data to do some math computation on it, right? And then maybe store it again after you update it. So if you access a data in a data structure or generally a variable, most likely you're going to access it again and again and again, right? As I have mentioned in one of the earlier lectures, it doesn't make any sense that you define a variable, give it a value, and then don't use it later on. Some compilers currently give you warnings that this variable is never used, right? So you should really remove it, right? Which means you define your variables, you keep using them again and again and again. This is called temporal locality. So recently executed instructions, likely to be executed again, this is about instructions. Again, think about inner loops, but also recently referenced data is likely to be referenced again soon, right? This is about temporal locality. We're talking about the same data element. Over time, it's most likely that you're going to access it multiple times. For spatial locality, we're not talking about that same element. We're talking about the adjacent elements, right? So if I want to draw, just to give you a visual reference to this, you think about an array again. Temporal locality is saying for element A0, for example, if I access it once, over time, if I access A0 here, most likely in the near future, I'm going to access A0 again. This is time. And then A0 again, etc., etc., etc. Good? But this is basic temporal locality. I'll talk about the same data over time. Spatial locality is saying if you access A0 now, most likely you're going to need A1 in the near future, and A2 might be, right? So A1 and A2 is the adjacent data to A0. This is why it's called spatial locality, right? They are close in space. Okay? Questions? So why you are discussing this? Why it's important really to identify there are temporal locality and spatial locality in modern applications? What do you think? Based on what we discussed so far, why this is something relevant to what we have been discussing about caches and the hierarchy and that stuff? Yeah?
So you can store relevant data in caches.
Yeah, exactly. Thank you. So given that if I have those locality concepts, maybe when I access an element, instead of every time I go, so if I go back to that level, now let's continue with the array example. Assume originally A0 was in the main memory. if the locality concept applies, instead of every time I go to the main memory to bring A0, in the very first time if I access it, if I bring it closer to the cache here, next time when I need it, I would find it in my L1. So I cut down the access time from the main memory 100x to the L1, which is few cycles, 1-2 cycles. Good. Also, instead of bringing A0 from the main memory to the L1, I can also bring other closer elements, right? Correct? With spatial locality. If I bring those closer elements, even in the first reference of A1, it will not be a mess in the L1 cache. It will be a hit. I will find it there. Why? Because I brought it applying the spatial locality concept. Make sense? So those locality concepts are materialized in the hardware by assuming that when I access the data, bring it closer to the CPU. Because when you need it again, you will find it. Okay? And also bring the closer data to that particular data that you access, which is a spatial locality concept, to also the closer to the CPU. Okay? Questions? Great. So if we understand this so far, we understand that we need a cache hierarchy, and we are leveraging the locality concepts in applications to be able to optimize the memory access time. What can we cover in caches? First thing, we need to understand that caches are hardware managed. What does it mean? It means that in your 2SH, 2SI, when you needed to write a program, you didn't need to understand what are the specifics of your cache architecture, right? You didn't need to understand that I have a 4 megabyte L3. Later on, as we will see, that it has a cache line of 64 bytes. You didn't need to do that, right? So it's software oblivious, which means all the management is done under the hood by the hardware. That said, it's very important for even a software engineer to understand the memory hierarchy to be able really to optimize your code, right? There's a lot of stuff that's being done by professional programmers that in fact show that the access time of an application can be improved by multiple X's by just tailoring your array in a certain way that you can access your memory fast, right? And there is a very, very seminal tutorial by a software engineer from Red Hat. It's a very old one, 15 years ago or something. The title of that tutorial, if I remember it correctly, it was called What Every Programmer Needs to Know About Memory. And he shows, and he was a pure software engineer, he's not a hardware engineer. But then he showed few examples of how, in fact, writing your application as a software engineer in a very certain way would impact, you can really get 200%, 300% performance improvement by only writing the software in a completely different way, if you understand your cache hierarchy and memory hierarchy, right? I will put a link to this tutorial just for your own reference, because it's very interesting to understand how does really the software and the hardware comes together. Okay? But again, it's hardware managed, which means I don't explicitly manage from the software. I don't say, go ahead as a cache, give me, I don't write an instruction or a line of C code that says, as a cache, please bring A2 to me because I need it, right? You just reference it, access it, load store instructions are being created in assembly, and under the hood, the cache hierarchy works. Okay? Great. And then, well, compared to this, in fact, something just as a side note, there are types of memories, SRAMs as well, in also some modern machines that are software managed. These are called scratch pads, right? Scratch pad memories are common in embedded systems, but surprisingly, they're also very common in gaming consoles, right? Like PS5 and Xbox. If you look into the actual leadership documentation, you will find that the software that is running under the hood, because software managed caches or scratch pads, they can improve your performance a lot if you guide them through the software, right? But as a user, you don't care about that. The actual firmware that is running on the gaming console is the one that is controlling them. Yes, and we will discuss this towards the end, because as I was saying, currently many of the ongoing research and also in industry, some of the things they're trying to explore is what if there are applications that in fact don't have very high locality? They have a random access pattern, for example. Think about linked lists or trees or graph processing, where you keep referencing things through pointers that you jump in the memory with no known locality. In that case, locality will not help. and current existing solutions in our machines are bad for performance. That's one reason why, for example, people don't run machine learning algorithms into CPUs. But people are trying to come up with solutions for that. One solution could be, for example, if you identify that pattern, you can bypass the cache. Don't really cache that, because if I'm not referencing, going back to the array example again, if I'm accessing A0 once and I don't access it again, there is no point of bringing it to the L1. So just bypass the cache, go to the main memory dial. So there are solutions, and it's an open problem right now. It's still an ongoing hot research area. What to do for applications that don't exhibit high locality. So you will see later on, if you end up working for an architecture company or in research, you will observe that many of the current open problems is all what we discuss currently in 4DM does not generally apply for modern applications, right? So what people have been building for decades, making the communities fast, leveraging locality, all these concepts that where our general purpose machines are built for, they don't really work for self-driving cars. They don't work for IoT devices. They don't work for machine learning algorithms. So they need to come up with new algorithms, new hardware and software. And I discussed with you earlier the hardware software co-design techniques, that how can I really redesign the hardware and software to really address some of these problems, right? But what we're discussing right now is the fundamentals, right? It doesn't mean, and this is a very good lesson, that we should always question things, right? Being a fundamental for 20, 30 years doesn't mean that it's always true. Computer architecture, people call it like it's a mix of science and art. So all the time you need to adapt. You need to basically be pragmatic. Well, sometimes you do stuff because most current existing applications will benefit from it. After 10 years, if the applications change, your hardware should change. It's not really a holy book, right? It's something that would change to fit the needs of new use cases. Good. So we said caches are hardware managed. This is important to understand. But then, some of the things we're going to discuss is what we call a cache organization. Here I'm giving the headlines, the titles of the things that we need to cover related to caches. There's something that's called the ABCs of caches, associativity, locks, and conflicts. We'll go through all of this. And then how we can really classify misses, and we'll see what does it mean to be a miss or a hit. And then what are we targeting? Good, again, everything goes back to the performance lecture. I'm trying to improve the performance as much as I can by reducing the misses into the closer levels of caches, like making sure my data is there all the time. Improve the miss penalty. What I mean by a miss is whether my data is in that cache level or not. If I find it, it's called the hit. If I don't find it, it's called the miss, right? It's a very common technique. And I believe we use the same terminology for branches, right? So if you think about the history of branches, it's nothing other than a form of a memory, right? It's an SRAM, it's a table. If you have a BTB miss, for example, or if you have a misprediction, that means your branch is not in the table, right? So you didn't find your data there. So a general concept for any memory, even for software lookups, you find your data in the lookup, it's called the hit in the lookup. You don't find your data in the lookup, it's called the miss in the lookup. Good? Okay. So this is what we call the miss classification, what type of misses we have. And then we aim to reduce misses as much as we can. And if a miss happens, I'm trying to improve the access time for the lower levels of memory. That's what we call later on improve miss penalty. And then we also want to make sure the hit happens as fast as we can. It doesn't make any sense to say, okay, I'm making sure my data is in the level 1 cache all the time, but for that reason, I'm going to make my L1 cache a gigabyte cache. Even if you put the cost aside. Why that's the case? Because we said there is a trade-off between performance, access time, and the capacity. If you make your L1 1 gigabyte, it means the access time will go from 1 or 2 cycles to 50 cycles. So your hit penalty, or your hit access time, or your hit latency will become right now huge, which is no good. Good. So we try to optimize all these trade-offs, as we'll see later on. Great. Okay. So let's stop here, and I will see you at 12:30, and we'll continue the cache topic tomorrow.